Streaming. There we go. All right, so now we are ready to go. So as I said last week, we are gonna start with the graph theory stuff today. So there's a little bit more to time complexity, but instead of going over all of that material, I think it's better to move on to talk about graph theory, and potentially we can hit predicate calculus after that. And if we have time left at the end of the semester, we can go back to recursive definitions and algorithms, and then how we can deal with categories of time complexity. Alright, so we're getting to graphs now. There we go. Alright, so I'm hoping you guys had some time to review the notes over the weekend, and potentially come up with some questions. Oh, okay, yes, the streaming link. Give me a second here. There we go. And I'm gonna pin it too. Alright, so there we go. So YouTube is up. I can see that running. Alright, so the first part of this module, module 310, is to talk about what is a graph. Okay, so we are going to use terminology that we already know to explain what a graph is. So the first part is, typically I use the uppercase letter G to denote a graph, and a graph itself is a two-tuple. Now this notation we have seen already, because when we talked about propositional logic, it's a five-tuple. So a graph is just a two-tuple. In a two-tuple, one part of the two-tuple is V, which is the set of vertices, and then we also have E, which is the set of edges. There's little restriction of the set of vertices. In other words, you can have anything in the set of V. You can have integers, you can have names of cars, you can have coordinates, on a map. You can have, basically, variables if you need to. When you're talking about compilers, you can have expressions, you can have, values in variables, values in registers, and so on. So V doesn't really have a whole lot of restrictions, as far as, what you can use as elements of V. Now E, on the other hand, the set of edges, now we have some restrictions. Because E has to be a subset, not necessarily a proper subset, but it has to be a subset of the Cartesian product between V and V. So that's the restriction that you need to play by, when we talk about the set E, which is the set of edges. So that automatically implies that each edge, or each element in E, is a two-tuple where the first item is a vertex, and so is the second item. That's also a vertex. So some literature, likes to refer to the names of each two-tuple of an element inside E. The first item is called the tail, and then the second item is called the head. I know this sounds really counterintuitive, but that's because we are looking at the two-tuple like an arrow, where the arrow is pointing from the first item to the second item. So if you think about the anatomy of an arrow, the tail is, basically the first item. In this case, this is where we're coming from, and then the head, the arrowhead, is where we're going to, which is the second item of an edge. So that's why, we call, the first item the tail, and then the second item the head, when we are talking about an edge. This also further implies an edge is directional. So, when you have only two vertices, like A, B, then you can have an edge from A to B, but you can also have a different and distinct edge from B back to A, because edges are directional. So, and that's part is, is discussed over here, because, ordering is significant in a tuple, And because an edge is a two tuple, so that means which vertex is the first one and which vertex is the second one, that ordering is important. So when we create a graph using directed edges or directional edges, it is called a digraph, which is the abbreviation of a directional graph. You can always make a non-directional graph using a digraph, because all you have to do is to make sure that every single edge has a counterpart. So when you have an edge going from A to B, then there's going to be an edge from B back to A. When you don't have an edge from A to C, you better make sure there's no edge from C back to A. So as long as we can use that method to create edges, we can have a digraph to represent a non-directional graph. The other way around is not possible. So there's no way to use a non-directional graph to represent a digraph. All right, so do we have any questions about these terms? Do we have any questions about the terms of what is a graph? What is the set of vertices? What is the set of edges? What is an edge? How do we call the first part of an edge? How do we call the second part of an edge? Do we have any questions about that? Okay, we got Yolanda typing, so I'm gonna wait a little bit.
Oh, I'm just going to ask.
Yeah,
Sorry.
go ahead. Yeah, that's fine.
Okay, so my question was, with the set E, we have the two tuple tail comma head. Is there a similar label used for the set V?
No, because in the set V, each element is just an element. Now,
Okay.
this is not to say that each element of V cannot be itself a tuple. I know that sounds confusing, but the whole point is whatever V you make, okay, E is the Cartesian product between V and V, or E is a subset of the Cartesian product between V and V. So you can make V, each element of V being super complex to begin with. It doesn't really matter, because whatever element that we put into E is a two tuple where the first element is coming from V and then the second element is coming from V as well. Is that okay? Let me give you an example. So nothing beats an example in these cases. So we're gonna use mousepad. Yeah, I should have set up my tablet to work in today's class too, but I didn't do it. So we're gonna use Notepad to look at these things. But I think in a certain way this is also beneficial. So we can make V itself already a set of two tuples. Okay, it doesn't really matter. We just have 1, 2, 1, 1, and 2, 1. Okay, don't ask me what they're representing. Okay, they're just elements in V. So now when we look at E, one potential E, because remember E is a subset of the Cartesian product of V and V. So we can now have 1, 2, and 1, 1. That can represent an edge. In other words, this 1, 2 is representing a single point somewhere, okay, a single element as a vertex. This 1, 1 is representing another vertex. Now, why is it represented as 1, 2 and 1, 1 instead of lowercase a and lowercase b? I don't know. I mean, I'm just using this as an example. Okay, so there's no restriction whatsoever of how the format of an element in V. Okay, there's no restrictions whatsoever. However, when we look at the set E, every element needs to be a two tuple, where the first element has to come from V, and then the second element also has to come from V. So that is the restriction that we place on E, because E has to be a subset of the Cartesian product between V and V. So I just picked the worst possible, the most confusing way to create a V as an example, and the matching E also as an example. All right, so do we have any other questions about this example? Okay, looks like there are no questions. All right, so in case there's no question, the last paragraph, which is a single sentence, all it says is, if we want to create a non-directed graph or undirected graph, we just have to make sure that we have duplicates of edges. Well, I shouldn't say duplicate, but mirror images of edges in E. So that way, if there's a way to go from one vertex to the other one, there's always a way back too. Alright, so Jack just posted something. So it's like V are the points and E are the lines. Yes, that is typically how, for a simpler graph, this is how we visualize or how we draw the graphs. But it does get complicated. When the graph gets complicated, it becomes kind of difficult to visualize just by drawing it. But for simpler ones, and just for understanding an algorithm, that's a good way. Okay, you just say, we just draw an arrow going from the tail to the head. In other words, we're drawing an arrow from the first element inside the two tuple to the second item in the two tuple for any edge, for all the edges. So that is correct. Jack is correct about that point. All right, so we are moving on to section 3. Section 3 talks about, terms, and it used to be a lot longer than this, but I found out that a lot of terms really are not needed in the discussion of the algorithms, and that's why, I do not introduce those extra terms that are really not needed. So the term that we really need to understand is a path. Okay, a path, in this case I use lowercase p, to name the path that we're talking about. In a graph is a tuple of vertices. Now there are alternative ways to define the path. You can basically use edges to define the path, or you can use vertices to define the path. But if we use vertices to define the path, then there are extra restrictions. So we'll go ahead and talk about these restrictions here. So a path in this case is really just a tuple of vertices. Now how many vertices are in this tuple? Well, it depends on the length of the path. Depends on the number of hops in the path. Okay, so if you have a path that has 3 hops, okay, then there are 4 vertices because you need one vertex more than the number of hops to define a path. And someone's going to be smart and go like, but what about a circular path? Well, the thing is you cannot have a circular path. So paths cannot be circular. So that means the number of vertices that you name in the path has to be 1 more than the number of hops. When we talk about a hop, it's basically just going from one vertex to another vertex. That's a hop. So edges from E must lead from one vertex to the next. Okay, so that's just a verbal definition. Okay, this is just a verbal way to describe the restriction of P as a tuple of vertices and when it can be seen as a path. So this is the restriction, and I'll read that one more time. Edges from E must lead from one vertex to the next in a path. That can be confusing. Okay, so in other words, we're going to use a mathematical notation to basically describe exactly the same thing. So what we're talking about here is for all I in the set of natural numbers. In other words, at this point, we just know that I is some kind of natural number, and that's the implication right here. Whenever we see an implication, we kind of need to evaluate the left-hand side first. We need to know what is the left-hand side trying to specify. In this case, the left-hand side is saying as long as I is less than or equal to, and then I use bar p bar to indicate the cardinality or the length of a tuple, much like we use bar p bar something to refer to the cardinality of a set. So that's really just asking how many elements do we have in the tuple that we know as P. And then we subtract 2. Now the reason why we are subtracting 2, okay, let's talk about subtracting 1 first. Subtracting 1 is needed because in C and most programming languages they are 0 oriented, which means the first item has an index of 0, which means the last item is going to have an index of the number of items in the tuple minus 1. So minus 1 is kind of a given if we want to only focus on indexes that are valid for this particular path P. But why is it minus 2? Well, the reason why it's minus 2 is because we also refer to I plus 1, the index plus 1 over here. So that means in order to make sure this makes any sense, we need to make sure that I is less than or equal to bar p bar minus 2 and not bar p bar minus 1. So this extra plus 1 here is the reason why we have minus 2 over here. So overall, okay, so let's kind of take a step back and understand what this restriction this restriction is really saying. So what this restriction is really saying is I is a valid index up to and including the second last item in the path, but not the last item in the path. The reason why that is the case is as long as I meets this requirement, let's talk about the second one. The second one says, well, if I is a valid index from the first item in the path all the way to the second last item of the path, then we better make sure that there is a two tuple of pi and then p bracket I plus 1 close bracket, which is basically just referring to two adjacent items in the tuple of path, and we better make sure that that tuple, that two tuple, is an element of E, which is an edge. So this whole thing combined is really just saying, every adjacent vertex. Okay, if you take a vertex in P and look at it, the next vertex in P, these two vertices, should be an edge. Okay, if you look at the first one as the first item of an edge and look at the second one as the second item of an edge, that should be an edge found. That should be an element found in the set of edges. Whew. Okay, that's a long way to say something that's rather simple. So do we have any questions about this requirement? What a path is? Just up to this point. The next paragraph, the next sentence is. I'll talk about that next. Okay, no questions. I'm just making sure that Discord is still running. Yes, it is. Alright, so the next sentence says a path cannot contain duplicates of a vertex. So that means, when you go through all the vertices in P, you better make sure that there are no duplicates. Then you might say, but that's the same thing as a set. No, it is still not the same thing as a set. Because in a set, even though we cannot have duplicates, there's no inherent ordering of how we list items inside a set. In other words, if you look at the set of A, B, C, okay, A, comma, B, comma, C in curly braces, it really is the same set as C, comma, B, comma, A in curly braces. They make no difference. But when you look at a path, okay, and A, B, C turn out to be vertices, and there are edges going from between the vertices that we are listing, then the path ABC is distinct from the path of ACB, which is distinct from CBA and so on, because the orderings are different. So just because a path cannot contain duplicates of a vertex, which means ABCA would not be a path, okay? It is called a walk, okay? So there are kind of confusing terms, but I'm not gonna introduce those terms unless we need to. So we'll just talk about path which cannot have duplicates of a vertex. Alright, so I'm gonna see if there are any questions up to this point. A path is basically just vertices connected by edges, and you cannot revisit a vertex in a path. That's basically the whole point. No questions? Alright. So in many graphs, we also define a distance function. So this is the notation that we have been using to describe functions. So D is the name of the function, E is our domain, and then R star is the codomain. So I use R star to basically refer to the set of real numbers that exclude all the negative real number values. So 0 is in here, okay? So 0 is non-negative, so it is in R star. But -1 is not, -0.5 is not, 2 is in R star, 5 is in R star, and so on. So that's a typical thing that we want to do, is to associate a distance between, for the edges. Now this distance is just a name. It does not necessarily equal to actual distances corresponding to points on the plane. Okay, it really is just a name of the function. So don't try to associate the distance function as actual distance. All right, So do we have any questions at this point? Just about the terms, what the
I have,
graph is, and then the terms. Go ahead.
yeah, I have a question.
Yeah.
So I noticed that you said that it's not a set. So we're not saving the values of path to any defined set. We're just iterating through
P is
the, sorry.
P is a tuple. It's an array
Okay.
list. So it's a list of vertices. But the restriction is between any two adjacent vertices, you better find an edge in E. So that's the only restriction.
Okay.
All right.
Thank you.
All right. So any other questions? Because if we don't fully understand these terms, it's really kind of difficult to describe and understand the algorithm. So it's kind of important that we understand all of these terms at this point. What is a graph? What is a vertex? What is an edge? What is a path? And what is a distance function? All of those are important at this point. No questions. All right. Well, if there are no questions, we're going to move on. All right, so now we are talking about Dijkstra's algorithm. Now, Dijkstra's algorithm is kind of interesting, and some of you who are taking CISP430 right now, or have taken CISP430 from Iraj, probably he has either started to talk about Dijkstra's algorithm, or he's done talking about Dijkstra's algorithm at this point. Am I correct about that? Especially for people who are taking CISP 430 from Iraj this semester. Okay, I don't see any responses, so I'm going to assume the answer is yes. Okay, someone is typing. Liu is typing, and so is Xavier. Very good. Nearest path. Sorta. Alright, so the way Iraj formulates his Dijkstra's algorithm is to find the shortest path between two vertices. The way I formulate my Dijkstra's algorithm is to find the shortest paths of all vertices to a particular destination vertex, or to a set of destination vertices. So my algorithm is definitely different compared to Iraj's algorithm. In the final exam, if I use Dijkstra's algorithm as a question, I will be referring to this algorithm. In other words, if the answer is based on Iraj's algorithm, it's probably unlikely to get any points. So you got to make sure that you can differentiate between the two, the algorithm that I'm going to talk about here versus the Dijkstra's algorithm that Iraj is going to talk about in his class. All right, so I just want to make sure that people understand that the two algorithms are different, and the way they work are different, and also the questions that I will be asking is based on whatever Dijkstra's algorithm is listed in the final exam question itself, which is likely to be the same as what we see in section 4, but I do not make any guarantees, so you have to be basically careful. You just have to be careful and just read the algorithm in the final exam to make sure that you understand what the algorithm in the final exam is going to do. It's very likely that it's based on this one, if not exactly the same as this one, if I choose to use Dijkstra's algorithm as part of the question. Any questions about that? Okay, all right. So we'll go ahead and start to talk about Dijkstra's algorithm first, and then we'll go ahead and trace through it just so that we know, how it works. So we'll describe the steps first. The first few lines all the way up to here, they're initializations. In other words, all they are doing is to make sure that we start with the correct values. The first line is not even initialization, it is describing the parameters. Okay, so if you think about Dijkstra's algorithm as a subroutine, as a function, or a procedure, or a subroutine. Okay, I think I said subroutine already. But if you think about it as a function in C, these are the parameters. So the parameter includes G, which is a graph, It includes d, which is a function to so that we can find the distances of the edges. It is also going to include a set S, which is a subset of V, and this is a subset of vertices identified as our destinations. So this is going to be the first major difference between the two algorithms, between the way Iraj is going to describe his Dijkstra's algorithm versus my Dijkstra's algorithm. So in this one, we have the ability to handle multiple destinations instead of a single one. So that's the first difference. And then the next two lines are initializations. So we are actually doing something. We're actually changing values of, I would say it's a function. Okay, so we're initializing, how we calculate the L values. So we basically say for each v, lowercase v, that is in the set S, which is a subset of v, and those are our destinations. L of v is initialized to 0. So the L value, so this is something that you can write down on your own because I'm describing this, but it's not in the notes. So the L value is basically the length of the shortest known path up to this point to from a vertex to one of the destination vertices. Let me say that one more time. Okay, so if you cannot catch all of this, not a problem. Okay, just jot down the time. The time is 12:29, almost 12:30. Okay, just write down 12:30 because I'm going to say that one more time. All right, so the L value or the L function is returning the length of the shortest path from, in this case, vertex V to one of the destinations. That is what the L value is in the context of this particular Dijkstra's algorithm. Alright, so knowing the semantics of the L value, now we want to see if this type of initialization is correct or not. Because remember, in this particular for each statement, we're only working with vertices that are elements of S. And element of S are basically each one is a destination. So if I ask you the question of what is the shortest path from a vertex that is known to be a destination to a destination, what do you think the answer is going to be? 0, because we are already at a destination, right? Let me give you an analogy. There we go. So think about Six Flags. Okay, the theme park. Yes. So think about the theme park, and think about you're taking a young person. Okay, possibly a niece, a nephew, your own kid, or some random kid that you pick up on the street and go like, hey, do you want to go to Six Flags? No, don't do that. Okay, but I'm just saying that you have a kid with you. Okay, you have a kid with you. You're going to Six Flags, and the destinations or the elements in S are the bathrooms. Okay, the edges are representing each vertex is representing a intersection. So when you look at the map of Six Flags, every single time you have an intersection where every time you can make a decision, oh, do we want to go this way or that way? That is a vertex. And the edges are connecting the vertices, so they're basically connecting the intersections. And the D function in this case, you can look at it as a real distance. Okay, you can just look at it as actual distance in feet, in yards, and whatnot. But I would more carefully and go like, okay, just look at this as how much resource is needed to go from one intersection to the next one, because you might want to take time into consideration. Just because two points are closer doesn't mean physically in terms of distance doesn't mean you can get from point A to point B in the quickest way just because it's the quote-unquote shortest in terms of distance. So whatever you want to do to define your D function is fine. Okay, you either use actual distance or time. Okay, and then remember each element of S is a bathroom. Okay, so what is Dijkstra's algorithm in this case trying to find? It is going to give you the shortest path from any intersection in Six Flags to the closest bathroom to that particular intersection. That is what this Dijkstra's algorithm is going to be able to accomplish. Now, if I remember correctly, um, Iraj's algorithm only has one starting point and one destination. So in his algorithm, the solution is basically just from one single vertex or one particular intersection to a designated bathroom, one of the many bathrooms in Six Flags. Whereas this algorithm, when it's done, it will basically say, okay, if you want to know how to go from any intersection to the closest bathroom to that intersection, we know how to do that. That is the result of this particular Dijkstra's algorithm. So you can kind of see, this one is more general. Okay, it doesn't give you just one shortest path. It gives you shortest paths from any vertex to a destination. So that's kind of cool. All right. So in that context, the third line is basically saying if you're already at the bathroom, it will take you 0 time to get to a bathroom. Does that make sense? In other words, when Timmy said, I need to go to the bathroom, you go like, but Timmy, we're already at the bathroom. That's basically that scenario for the third line. So the fourth line is basically saying for all of the other vertices, in other words, for all the other intersections in Six Flags, we just make the assumption that it is in the distance to the nearest bathroom is infinity, or whatever maximum number you can specify. So this is basically a pessimistic assumption to basically say until I actually find a path from this intersection to a bathroom, we're going to assume the distance is infinity. In other words, it's not connected to, it's not reachable. Okay, a bathroom is not reachable from this intersection unless we confirm that we just found a path to do it. So do we have any questions about the first 4 lines of the algorithm, including the first 2, which are the parameters, the second 2, which are loops to do some of the initialization, and most importantly, what is the L value representing? Do we have any questions about all of that stuff? Okay, I'm not seeing any questions, so we're going to move on. All right. Now, if you need more time to formulate a question, you can type in the text channel, just to let me know that you need more time, and that's perfectly okay as well. So don't worry if you say, I just need more time to formulate a question, because I know there's a question, I just don't know how to verbalize it yet. So that's perfectly okay if you want to, ask a question or just kind of.
I got a question, Professor.
Yes, go ahead.
So for the fourth bullet there, the way I initially interpreted it was that we are selecting a two-tuple named V, and what we're doing is, since we are removing all of the vertices that are in the set S from possible values to be compared to with the V minus S notation, we're just like setting this to this really high value, assuming that if there is a path, we'll never select it, or that we're going to write a condition that if the value returned is like the max value of an int, then just assume it's not a valid vertice.
Okay, first of all, there's no guarantee that we're dealing with any tuples here, because V is just an element of V minus S. Lowercase v is an element of uppercase V, which is the set of vertices minus S, and S is known to be a subset of V. So there should be no tuples whatsoever, in this entire discussion of, on the fourth line.
Okay.
So I'm not really sure, where the tuple is coming from.
I was looking at what I had kind of questioned when I was reading this. So thank you for that clarification. So then
Okay.
my initial way of interpreting this is we're going to get the set of vertices from all the possible values and okay, like the set of elements, I guess, in that represent vertices, and we're going to remove those from the possibility of being compared against V. And so everything that we're evaluating is everything that represents not a valid vertice, and we're setting that to a
Wait. Okay, hold on. Because V is still an element of V minus something, and V is representing all the vertices, so we are guaranteeing lowercase v is a vertex to begin with. What it is not is a destination, because the set S is the set of destinations. And since
okay.
S is excluded from V on the fourth bullet point when we're doing the for each, so this is basically saying for each non-destination vertex, do the following. Associate the L value to be infinity because it is not the destination itself and we haven't explored any edges. So let's just say that it is not connected to a destination at this point. That's
Okay.
basically what it is saying.
All right. Thank you so much.
Sure. All right. So any other questions about the first 4 lines of the algorithm? No questions. All right. So let's move on to Q is initialized to S. So whenever you see a left arrow like this, the left arrow is just assignment, which is a local variable to be the same as the set of all the destinations. So this is just initialization. I call the set Q the boundary vertices, but we'll see when we run the algorithm what it actually does. Okay, but it's just initialization. That's all it is. And then the next line is E prime equals to an empty set. This is the set of the quote-unquote solution edges. Now, since we haven't really run any algorithm at this point, there's no solution. So the solution is an empty set at this point. So all of these lines, all 6 lines at the very beginning, they're basically just specifying the parameters and go through some initialization so that we'll be ready for the actual algorithm, which is the while loop on the 7th bullet point. So I'm going to give you guys a moment to kind of make sure that we understand all of these steps here, what each variable is and what they're doing so far in the algorithm before we get into the algorithm. So I want to see if you guys have any questions. Alright, so I don't see anything in the text channel, no direct message, so I'm assuming that we don't have any questions about the algorithm up to this point. So now we get into the thick of it. Okay, this is the thick of it. So the algorithm does not terminate as long as Q is not empty. So as long as there are some elements in Q, we're not going to stop. The next line inside the loop, so I'm using a more or less Python approach here. So instead of using open and close curly braces to mark the beginning and the end of a block of code, I'm just using indentation because that's easy to do in LaTeX. So I was just being lazy when I specify the pseudocode in this case. So the first line inside the while loop says select v, this is lowercase v in Q, such that for all w in Q, L of v is less than or equal to L of w. Alright, so the rest is comment. Okay, so from here on it is just comment. So we want to look at just this part here, okay, just this part, the quantified expression, and see if we can figure out what that means. Okay, the quantification is easy to understand. We are only concerned about elements of Q. Okay, so if something is in V but it is not in Q, we are not interested. We don't need to deal with that. Okay, so we're only interested in elements of Q. and we want to select a v such that it meets this particular requirement. So what requirement are we talking about? So let's just say that you have picked a particular vertex as v. Okay, then you have to subject that vertex v, to this particular criterion, and see if this criterion is going to return true or not. So what this criterion is going to do is to say, okay, let's look through every single vertex that is in Q and make sure that the L value of V is less than or equal to the L value of W. So what it is really doing, if you use plain English, is it is selecting a vertex in Q that has the least L value. That is basically what this statement is trying to say. All right, so do we have any questions about the first statement inside the while loop, trying to select a vertex in Q where it has the least L value compared to the other vertices that are also in Q? Okay, yeah, go ahead.
Okay, so my like initial thought with this was, what are we just like iterating through the natural numbers for values of W? Because I know that we're like selecting a V in Q, and then we're yeah.
But we don't have any natural numbers. There's absolutely no natural number mentioned in here.
Okay.
Yeah, so we are just looking for the vertex that has the least L value at this point. But if
my question is, how do we iterate? How do we select the W's? Because just how do we select the W's? What are the conditions in this?
It's going to be a for each loop in a particular programming language that allows you to iterate through all the elements in the set. Okay. And I mean, it depends on what programming language you're using. So I'm translating all of the operations into set operations.
Mm-hmm.
So that's why I use for all W in Q as kind of the quantified statement here. So you in return have, if you are to implement this as an algorithm, you're going to have to think about how you're representing a set. Now some people are going to say, but Tag, we don't need to use a set to represent the vertices. We can just use a linked list. Okay, fine, use a linked list. Okay, but at the end of the day, okay, we are just basically saying, we eventually have to boil down to the implementation detail. Okay, if you want to use a fixed size array along with a length to represent a set, that's fine. If you want to use a bitmap approach to represent a set, that's fine too. If you want to use a string, like a C string, to represent a set because all the elements are printable characters, each one, fine, that's okay too. So it doesn't matter because I'm not specifying the low-level detail of how to implement all of these operations. All I'm saying is from the high-level perspective, I'm looking at Q as a set. Now, how you want to...
For the weekend, I was just reading this and I started trying to like implement this, and I just was running into like, oh, well, wait a minute. That was just one of the questions that I ran into while I was trying to. So I appreciate you going through that, because that helps me when like I'm trying to determine, like that I now understand what I'm doing with W.
Okay.
Thank you a lot.
Yeah, and this W is local to this particular statement too. So this W is not visible throughout the rest. So this W over here, it's not the same as this W.
Okay, because that's what I was thinking. Am I using that W down there to... Yeah, okay, thank you.
Sure. All right. So, just one more thing about programming languages. In certain programming languages, like JavaScript, it does have quote-unquote a built-in type of a set, which is kind of handy because now we can use the for each, which is a member function of a set, to kind of go through, iterate through all of the elements in a set. So that's kind of handy if you have a programming language that has provisions to deal with the higher level concept of a set. So Q was initialized to the set of all of the destination vertices. But depending on which iteration you're in, we don't know. I mean, Q is really just a set of vertices that just had their L value set to something smaller from infinity. So that's basically what Q is representing. Q is a set of vertices that just got their L values updated, quote unquote. Okay, quote unquote, because because in this case, the way we initialize, the L values, they're the destinations and the non-destinations are initialized just differently. But generally speaking, Q is a set of vertices where their L values are just updated. Does that answer the question, Jack? Okay, all right. It's difficult to answer the question, what exactly is Q set to at this point because it's inside a loop. Now, if it's not inside a loop, then it's easy to answer because the flow is always just coming from the initialization into the code that we're talking about. But because this is a while loop, it depends on how many times we have gone through the iterations. So we are looking for what we call the darn it, I cannot remember the term. There's a term invariant. That's it. We're looking. So what you're really asking is the invariant condition of a loop. And the invariant condition of this particular loop is more or less, sort of, the elements of the vertices, that has just gotten its L value updated. Okay, so that's kind of what the invariant condition is when it comes to describing Q. Alright, so moving from the first line to the second line inside the while loop. So the second line is Q gets Q minus the set that only has lowercase v in it. In other words, once we have selected the vertex in Q that has the least L value, we take it away from Q. Okay, so we don't get so this way we don't reconsider that vertex in the next iteration. Now, the next question, someone is going to have this in their mind automatically because I know some of you are very curious and inquisitive and you can think and go like, hey, what about this? So I can kind of guess someone may have this question, which is, once we remove a vertex from Q, is there a chance that we can put it back into Q? The answer is yes. Okay, so there is a way, there's a chance that a vertex can be reintroduced into Q after the second step in the while loop, after it is selected and removed because it has the least L value. There's a chance that it can be put back or added back into Q. So we'll talk about that, and we can hopefully go through some examples, maybe today, maybe not today, that would kind of illustrate how that can happen. And then what we have next is a for each loop. So this is a for each loop, which is in some way sort of like the for all thing, except in this case it is not a condition. We are not evaluating a condition. We are basically saying, okay, for every single edge E like this, we want to do the following. So now we have to look at the set, okay, this particular ad hoc set. Now I use the word ad hoc, just because, this particular set is defined on the fly in order, we are basically qualifying what edges should be in this ad hoc set as we evaluate this loop here. So the ad hoc set, which is starting from this curly brace ending with this curly brace over here, is described as every element in the set is in the form of WV. Now in this context, W is not bound to anything, so W itself is an unbound variable, but V is not, because V is bound from here. Okay, the first line after in the while loop is already binding V to a specific vertex. So V is already fixed. So we are basically looking at elements in E, which is the set of all the edges, where the first item in the edge is some W. I don't care who that is, but we need the second item to be V. In other words, for every single edge, where V is the head, it has those edges will have to be included in this ad hoc set description. And then we are looking at all of those edges, so that for each of those edges we can do the following steps. Alright, so I'm gonna pause here just to make sure that we understand what the for each line is doing. Okay, what edges are we working with in this particular for each loop? So I'll just kind of pause and make sure that you guys understand this, and if not, now will be a good time to ask questions, because then we're going to move in to the nested code within the for each loop. So I'm just looking at the clock right now just because I want to time myself. Alright, so I'm not seeing any questions. Okay, so now we are looking at an edge WV. So this time, W is bound to be a specific value, so that we are looking at a single edge that ends up at vertex V. In other words, okay, the other way to describe the for each line is to basically to say for each incoming edge to vertex V, do the following. Okay, so I'll say that one more time, and if you want to time mark this, it is 12:55 right now, and the for each loop is basically saying for each incoming edge to vertex V, do the following. Alright, so with that said, we're going to say, okay, what are we doing? The incoming edge is known to be WV, so W is the vertex that is connected to vertex V by an edge. And now we're trying to compute L of V plus D of E, this is E here, and we want to compare that to L of W. And if it is less than, then we do the following. Okay? So now we need to pause and understand, okay, what are we comparing? What is the significance of this comparison? Once again, write down the time mark, because you might need to refer back to this, when you are trying to understand and read the algorithm, or when you're trying to trace the algorithm. All right, so let's recall what is the L value of something. The L value of a vertex is the length of the shortest path from that vertex to a destination up to this point of the algorithm. That's what the L value of a vertex is. So L of V, if I were to apply the definition of L to V to L of V, is this portion is simply saying, this is the length of the shortest path from vertex V to a destination at this point of this algorithm. Okay, sort of, right? I mean, it's just the length of the shortest path, more or less, from V to a destination. And we are adding to it the distance of E. So on the left-hand side of the comparison, what are we getting? We are getting the length of an alternative path from W to a destination. That is what the left-hand side is representing. And then someone's going to say what again? Okay, so let's look at this edge here. This edge is going from W to V, and we already know that from V to a destination, the shortest path is going to be L of V. So when we add the distance of the edge WV to the shortest path, or to the length of the known shortest path at this point from vertex V to a destination, we are now computing the length of a alternative path from W to a destination. But Tack, why didn't you just say the shortest path? Because I don't know whether it's a shorter path or not. Okay, so that is why we have to compare the cost, or the length of the Okay, let me say that one more time. That's why we're comparing the left-hand side, which is representing the length of an alternative path from W to a destination, to what? To the L of W. To L of W. L of W is the length of the currently known shortest path from W to a destination. So now we are saying, is this alternative path shorter than what we have found before? That is what the condition is trying to find out. So I'm going to pause again to make sure that you guys understand the semantics, the meaning of this comparison. Why is it important? What is on the left hand side, what it is representing, and what is on the right hand side, what it is representing. Alright, I'm not seeing any questions. So obviously you guys all studied over the weekend and really got to the algorithm and got a good understanding of it already. So it is possible that the L value is not the length of the actual shortest path. It is simply the shortest path discovered up to this point of the running of the algorithm. That's what the L value is representing. Right, so I think that might answer the question of Garrett. Okay, there we go. So it is very important to understand that's what the L value is representing. It's not representing the length of the actual shortest path. It is representing the length of the shortest path discovered up to this point of running the algorithm. That is the important part, okay? All right. So if the condition is true, that means we just found a shorter path, right? Because we looked at the path formed by going from W to V as a single edge, and then from V all the way to a destination, which we don't really know how it works, but we know the length of that particular path is L of V. So that is a path that has a shorter length compared to what we have seen up to this point, because what we have seen up to this point has a length of L of W. So when the left hand side is less than the right hand side, then we know that we just found a shorter path from W to a destination. So what is the first thing we do? Well, the first thing we do is to update L of W. So L of W continues to reflect the length of the shortest path discovered up to this point of running the algorithm. And then the next one is a little confusing. Okay, it basically is just removing the edge of WU for some U. So we are basically removing from the E prime, which is the solution set of edges, to say, okay, what we have previously discovered as a part of the shortest path from W all the way to a destination, guess what? We got to erase that now, because that was not actually the shortest path, because we just found a shorter path at this point. So the for each loop here doesn't have to be a for each loop. I think there's only up to one edge in E prime that you can remove up to this point. But I'm using a for each loop just to say, hey, if you find any edge in E prime that starts with this particular vertex W, get rid of it. Okay? In other words, all the outgoing edges from W in E prime should be removed, because they are not going to be on the shortest path, because we just found a shorter path. Okay? So after we remove all the edges in E prime that really should not be a part of the solution, then we use the next line, which is the third line inside the if conditional statement, is to say, well, now we need to add WV as an edge into E prime. Well, I shouldn't use the word add, because this is technically a set union operation. So we have to compute E prime union with the set that has WV in it, because guess what? WV is now confirmed to be a part of the shorter path from W to a destination. In fact, it is the shortest of all the paths that we have discovered up to this point. So that's why we are using this union to update E prime itself. So the E prime is now including the proper edge going from W to a destination as a part of the shortest discovered path up to this point. Excuse me. And then the next line, which is the last one, is this is how we put something back into queue. This is how we add elements to queue, because we just updated the L value of W, making it smaller. And then someone's going to say, but Tech, how do we make it smaller? Well, we made it smaller because we wouldn't be here unless this condition is true. If this condition is true, that means we just updated the L value of W, so it becomes smaller. That is how we put things back into queue. Is every single time you identify and go like, hey, we just found a shorter path from this vertex to a destination, put it back into queue, because now we want to look at all the incoming edges to the vertex that just got a shorter path to the destination, because that can potentially lead to a shorter path from all of those other vertices going into the vertex that just got a lower L value. Yes, the time arc may be important here because I just said something that really describes the algorithm. It really describes the mechanism of this algorithm. What is queue tracking? Queue is basically tracking vertices that just got a lower L value, so that we can potentially look at all the incoming edges into those vertices and see if that change of the vertex that just got changed lead to changes to other vertices as well. So this kind of circles back to Jack's question at 12:48. Thanks to Discord, I know exactly the time, or at least down to the minute of that question, because that is what Q is trying to track. And this kind of ties in the whole algorithm, so that we hopefully we understand the mechanism of the algorithm, what each line is trying to do in the context of the algorithm. When the while loop is done, which means Q is empty. Now, what does it mean when Q is empty? Q is empty when we cannot find a path that is shorter from any vertex to a destination. Well, doesn't that mean whatever we have discovered is the shortest? Yeah. So that kind of makes sense, right? When Q is empty, that means we have already found the shortest path from any vertex to a destination vertex. So when that is done, when Q is empty, we get out of the loop, and then we just come here and go like, okay, now we just define a new graph. I call it the solution graph. So the solution graph G prime uses exactly the same vertices as G itself, but instead of using E, which is given to us as a parameter, it is using E prime because E prime is the set of the solution edges. So G prime is basically a quote-unquote subgraph of the original G, with some of the edges, potentially some of the edges gone. Not always, because if G is representing a linear graph, basically A goes to B, B goes to C, C goes to D, then it's going to be E is going to be the same as E prime, because there are no alternatives to talk about in that case. All right, so Anita has a question. Well, there are no such thing as a dumb question, so don't worry about that. What are L and D going to be functions in this program, or are they just variables? Okay, so that's a very good question. D is definitely a function, at least in concept, but how you implement that is up to you. L is a little bit different. It is supposed to be a function, but it makes it kind of awkward, okay, as a function, because if you look at L as a function, then you have to kind of think about, okay, but what is the domain and what is the codomain of L as a function? The domain is not difficult. The domain of L would be just uppercase V, because we are mapping from a vertex to the length of the shortest discovered path up to that point of running the algorithm. So the domain is easy, okay? The domain of L is just uppercase V, the set of all the vertices. The codomain is the difficult part. The codomain would appear to be, oh, can't we just use the same codomain as D, which is just R star, all the non-negative real numbers? The answer is no. The answer is no, because infinity is not really an element of R star, because infinity is not a value. So, so the codomain in this case, for L, is going to be R star, and then you have to explicitly use a union to include infinity as an element of it. So it just gets a little bit awkward. It's just awkward. I mean, it's not. But yes, but once you do that, okay, once you do that, then L really is a function. So when we change L of something, these are just initializations, so they're not too big of a deal. So we are just adding things to L as a set of two tuples. But when we update it like this over here, we are taking out a two tuple first, and then we place it with another two tuple. So from that perspective, you can look at L just as a set, okay, as a set of two tuples where the first item is a vertex and the second item is a non-negative real number or infinity. So from that perspective, you can look at L just as a function, just like D is a function. Okay, so I have just mentioned, what L really is, but that's conceptual. Okay, it's a function. What D really is, but that's also conceptual. But in reality, when you're implementing this as a program, okay, how are you going to do this? Well, that's a very good question, isn't it? Because D is not going to be an arithmetic function where you can say, oh, D of something is just a closed form formula. Okay, something times 2 plus divided by something and then add some constant to it. No, it's not going to have a closed form because D is going to be somewhat arbitrary. Okay, it can map any edge to any non-negative real number. Okay, so you still need a way to represent it if you are to run this as a program. Okay, I thought, okay, Garrett just typed something. So okay, this is what this is coming from Garrett. Is it correct to think of this algorithm as a way to quantify vertices and destinations, and a way to navigate between these points with the shortest path function? Regardless of how crazy the graph G could be, I imagine G can be quite different from the standard graph we were used to drawing in calculus classes. Oh yeah, the graph that we are talking about here has nothing to do with the graphs in calculus classes. I would say, okay, if you want to think about a graph in this case, you can look at one thing you can do is to just go to Google Maps. Great, I don't have access to Google Maps because it is not a part of the. This is funny, right? Okay, so let's just look at the map. Okay, map of Sacramento. Who would have thought that I would not have Google Map access just because I signed into the Los Rios app, apps.losrios.edu account? That is just strange. Okay, yeah. So I think you got the point, right? So the idea is, if you look at each intersection as a vertex, then each line connecting connecting from one intersection to the next intersection is an edge. So as a result, this is a graph. I mean, this is your graph. And also remember what we were using as an example in today's class. Okay, so we have Six Flags map. Okay, and we want the Vallejo one. Vallejo. And let's see. I mean, you guys probably get the idea, but I want to get to it. I'm not going to download the official mobile app because it's useless on a PC. There we go. Alright, so now we can zoom in. Alright. Not really the best kind of resolution, but it's good enough, right? So if you think about each intersection like this, like this, like this, like this as a vertex, then the path between the two intersections is an edge. So that is the kind of graph that we are talking about. Now, in this particular case, it is more or less a symmetric, graph, which means going from the time going from point A to point B and the time going back from point B back to point A would be the same. But if you think about a more extreme situation where Six Flags is not flat, okay, it is actually hilly, then it is asymmetric because going uphill and going downhill is not going to be the same. It's not going to be symmetric. Okay, excellent, excellent. Well, this is just an example. Graphs in general are not even going to correspond to coordinates, two-dimensional or otherwise. Um, so, okay, I can talk a little bit about graph theory and how it is applied to compilers of all things, right? So, if you look at compiler register allocation graph, okay, there we go. So if you just look up your Wikipedia on register allocation, and then in this article you look for the word graph, you can see how it has mentioned, what, 51 times. And that's because we can use a graph to represent, how a register changes, how it is utilized by expressions. So when we want to optimize a compiler and go like, hey, this architecture has got 32 general purpose registers, we don't need to keep things in memory and keep reading and writing to memory. We can keep certain things in registers, so the access to that information or that piece of data is going to be fast, during the execution of a subroutine. So that's what register allocation is all about. Is which register should be used to remember which expression while we are going through the code of a subroutine. And the call graph is representing subroutine A is calling subroutine B and C and D, and then subroutine C is calling subroutine F and G, and then G is calling H, and so on and so forth. So that is a call graph. It is not a tree, okay? It's not a call tree because potentially you can have a recursive subroutine, and that's why it is just a general graph, because you can have loops going back to a function itself. But you can, if you look up the word graph in here, you can see it mentioning several times. But this kind of graph has nothing to do with two-dimensional or three-dimensional um, coordinates, okay? Because we are not actually measuring the distance. We are measuring the expense, okay? How much time do we need to recompute something? That becomes the quote-unquote distance function in these cases. Now, since we're here and we have 2 minutes left, so I can't really give you a demonstration of the algorithm today. However, I can talk about a concept which is NP complete. Okay, yeah, sure, you can do that. But NP completeness is an interesting thing. If you click on this one, you will find out what it means. But if I were to summarize, okay, I can summarize NP completeness in 2 minutes. If something is classified as NP complete, if an algorithm is classified as NP complete, it means it is a very tough problem to solve. It would be transformable using not linear time, but polynomial time. It would be transformable to become the traveling salesman problem. So in this case, register allocation is an NP complete problem, which means in general, it takes a huge amount of time to solve the problem. It doesn't mean the problem is not solvable, it just means it takes a lot of time. And NP stands for non non-deterministic polynomial. So the n is coming from non-deterministic, and then p is polynomial. So polynomial, we just talked about time complexity, right? So polynomial simply means it is a big theta of n, which is lowercase n, or the size of the problem, to the power of some constant power. So it will be like n to the power 3, n to the power 4, and so on. So you would say, well, it doesn't sound too bad, right? Well, the problem is not coming from the p part; it's coming from the n part, because n is a non-deterministic. The best way to visualize non-deterministic means is you basically have the capability to instantaneously, with no overhead whatsoever, to spin off a new actual core in the processor whenever you need to. And there's no upper limit of how many cores you can instantiate with no overhead time whatsoever. So if you have a magical processor like that, then this kind of algorithm will take polynomial time to finish. That is what NP complete means. So, well, not exactly, but the gist of it, okay? Because the complete part also has a meaning. So, but I'm running out of time today to talk about that. When you move on to a 4-year university, which I know you will, okay, you're going to take a class in. There are two classes that will talk about this. One is the analysis of algorithms. It's all about the time complexity of stuff. You might see the same thing again in computational theory, which talks about Turing machines and whatnot. So there's a particular context in that one that might, actually, mention NP complete as well. So these are kind of high-level concepts, but the application is rather simple. Okay, it just means something is really hard to solve. All right. All right. Mm, I'm not sure about that, Angel. I will spend some time to think about that one. But we are out of time today. I will see you guys on Wednesday. Yes, so we're going to go through examples, on Wednesday, because I'll have my tablet hooked up to my PC again at that point, so I can actually draw some graphs, because I think it's easier to follow a graphical representation of a graph as we talk about the algorithm. So it's going to be interesting. It's going to be fun on Wednesday, because what we'll do is we'll show the algorithm on one side. I may not do that because you guys all have your own computer, right? So you can basically have your web page to be on the algorithm itself. And then I'll have one spreadsheet open because I want to trace using a spreadsheet because it has got rows and columns. And then we'll also have one screen on the actual graph so that we can actually see, oh, this is where vertex A is, this is where vertex B is, and the cost or the distance between A and B as an edge is blah blah and so on. So it's easier to understand the algorithm when we can see the graph. That's what we're going to do on Wednesday. And when we have time, we'll move on to the A star algorithm, which is sometimes better than the Dijkstra algorithm. Alrighty, so we are ending today's class right now. I'll see you guys on